how to describe these carbon-carbon bonds. So in the first case of this first bond here that I've put in a square, what type of a bond is this? Is this sigma or pi? Yep, it's a sigma bond. We're having two orbitals coming together on the bond axis. So we'll call this sigma, and it's between two sp2 hybrid carbon atoms. So it's sigma carbon sp2, carbon sp2. What about this second bond here where we're going to have interaction of two p orbitals? Is that sigma or pi? Pi, great. So our second bond is going to be a pi bond. And again, this is between the p orbitals. These are not hybrid orbitals. So when we name this bond, we're going to name it as a pi bond here because it's between two p orbitals. And it's going to be between the carbon 2py orbital and the other carbon 2py orbital. Remember, we didn't hybridize the 2py orbital, so that's what we have left over to form these pi bonds. All right, so in addition to having these two carbon bonds, we actually also have 4 carbon-hydrogen bonds in addition to our carbon-carbon bonds. So why don't you tell me what the valence bond description would be of these carbon-hydrogen bonds? So let's take 10 seconds on that. Okay, great. So most of you got it. So we can switch to the notes and let's talk about this here. So in terms of the carbon-hydrogen bond, it's a sigma bond because we define it at any time we are bonding to an atom, we have to keep redefining our bond axis to whatever two atoms we're talking about. So it's along the bond axis, and it's between a carbon sp2 hybrid, and then the hydrogen is just a 1s orbital that we're combining here. So those are our 3 types of bonds in ethene. One thing that I want to mention that is really important is once you have double bonds, what happens between those two atoms in the molecule is they can no longer rotate in relation to each other. So you can think about why that is. When we have just a single bond in a molecule, you have all the free rotation you want. You can just spin it around. There's nothing keeping it in place. But once you have a double bond here, we have our pi bond as well as our sigma bond. So there's electron density above the molecule, or above the bond and below the bond. So if I try to rotate my two atoms, you see that I have to break that pi bond because they need to be lined up so that the electron density can overlap. So in order to rotate a double bond, you have to actually break the pi bond. So essentially what you're doing is breaking the double bond. So really, you cannot ever rotate a double bond. It makes your molecule very rigid. This is incredibly important because if you picture having a double bond in a very large molecule, you could have all sorts of other atoms off this way and all sorts of other atoms off this way. And you can picture the shape would be very different if you have one conformation versus another conformation. So it's very important that the double bond locks it in a particular conformation. This completely could change if you were to flip from one to the other conformation, which can happen in chemical reactions. If you were to make that change, you would find that the molecule now has completely different biological and chemical properties. And so it's very important to be keeping in mind that anytime you see a double bond, you have a pi bond there, so you're not going to see any rotation around the bond axis. All right, so let's think of a more complicated example of having a double bond and maybe a more interesting example, and this is talking about benzene. I think most of you have talked a little bit about benzene over this past week in recitation. Benzene is a ring that's made up of 6 carbon atoms and 6 hydrogen atoms. So let's picture what this looks like here, and we'll start with 4 and we'll add in our last 2. So essentially we have 2 ethene or ethylene molecules here to start with, where these blue are our 2 sp2 hybrid orbitals. So you can see that for each carbon atom, one is already used up binding to another carbon atom. If we think about bringing in those last 2 carbons, what you can see is that for every carbon, 2 of its hybrid orbitals are being used to bond to other carbons. So that leaves each carbon with only 1 hybrid orbital left. And if we think about the 6 hydrogens, now each of those are going to bind by combining one of the carbon hybrid orbitals to a 1s orbital of hydrogen. So if we think about what bonds are in this molecule, we actually have 6 of these sigma carbon sp2 bonds. We also have carbon sp2 hydrogen 1s bonds. How many of those do we have? Yep, we also have 6 of these because we have 6 carbon-hydrogen bonds. So that's 2 of our types of bonds in benzene, and we have 1 type left, and that's going to actually be the double bond, or the pi bond, that forms between some of these p orbitals. So we can have 1 bond here between this carbon's p orbital and this carbon's p orbital. So let's have a clicker question here on how many total pi bonds do you expect to see in benzene? And actually, oh, good. So it's left up. The notes are left up on this screen right now. All right, so let's take 10 seconds on that. All right, great. So most of you saw that what we would expect to see is 3 bonds. Some of you thought 6, so let's take a look at why 3 is correct. So what we end up having is 3 of these pi, 2py, 2py bonds. We can have 1 between these 2 carbons here. Can we have 1 between these 2 carbons here if we have 1 here? No, we can't. We're already using it up in this pi bond here. So that means we're limited to only 2 other spots on the molecule, so we have 3. But of course, what you saw in recitation, and hopefully what you can now think very quickly by looking at this, is that this is not the only configuration of pi bonds that we could have in benzene. There's absolutely no reason I couldn't have switched it around and said that instead the pi orbitals form between these atoms instead of those first atoms I showed. So let's look at this in a more simple structure here, where we have the 2 possible forms of benzene. And the reality is that it's going to be some combination of the 2. This is resonance. This is a case of a resonance structure. So what we see is that those 6 pi electrons are actually going to be delocalized around all 6 of those atoms. So if you think about any one of these carbon-carbon bonds, what type of a bond would you expect that to be? What would the bond order be for this bond? Yep, it's going to be a 1.5 bond. It's a 1.5 because it's halfway between a double bond and a single bond. So of course, this is resonance, so we can go ahead and put our resonance notation in there to indicate that benzene is a resonance structure. All right, so let's quickly